All right, welcome to the. Right, here we go. The chlorine can be prepared by the following reaction. I want to know if I can do this and send them to you. Do you understand me? So this is a test, but you've all got the papers, so you can keep up with me. Yes. So scribble stuff down as we go along. But we're not going to learn chemistry. We're just learning revision. Is that okay? Yeah. All right. So explain why manganese dioxide here is described as an oxidizing agent in the reaction. Now, obviously, we've got to prove this oxidizes something. Okay, so let's have a look. If we look at the chloride here, this has an oxidation state of -1 there. And if you look at the chlorine on the right, it has an oxidation state of 0. Is that clear? So the chlorine, or I should say the chloride ion, has oxidation number equal to -1, and the chlorine has oxidation number equal to 0, and therefore the manganese dioxide is an oxidizing agent. Makes sense? Yes? Now that's one way around we could look at it, but another way around we could look at exactly the same problem is we could look at the manganese dioxide itself. Yes? If it is an oxidizing agent, what must happen to it? Exactly, it must be reduced. And let's just show the manganese dioxide is reduced, or Mn on the left is +4, yes, and on the right is +2. So another just as valid answer would be the Mn has gone from oxidation number of +4 to +2. So the manganese ion has been reduced. And if something has been reduced, it therefore, by definition, must be an oxidizing agent. Are we all good? Now, for extra marks here, let's have a look at these balancing. Have a look at this. This went from +4 to +2. In other words, that went down by -2. What did the chlorine do? It should have gone up by +2. Do you follow me? Yeah. And now, if you look at this, it looks like Cl has gone to Cl. It looks like four of them. It looks like four Cl minuses have gone to Cl2. Yes. And that would be a an increase of 4 when I've just said there should be an increase of 2. Do you follow me? But if you look closely at the equation, two of them don't get oxidized at all. Can you see that? So only two of these get oxidized. Two do not. Does that make sense? Yeah? All right. State what you would observe in this equation. Well, what do you think you'd see? There's not a lot going on here, is there? But I would pick the solids going into solution. In other words, I'd simply say the solid dissolves. Okay. Now, it's possible also we're going to get a green gas evolved. Do you see that? So if there was 2 marks available, I'd say green gas evolved. So there you go. I can't think of anything else to say, but that's more than enough to say. Okay. So the halogens are chlorine, bromine, and iodine. They're all volatile. What do we mean by volatile? What's a volatile? What does volatile mean? This is too big. Anyone? Yeah, it forms, it easily forms vapor. Okay. So what happens to the volatility? What happens as you go down the thing? It decreases. Thank you. Right. So as you go down, the volatility decreases, yes. And that's because the van der Waals forces decrease going down. Oh, do they increase? Oh, you're making. Yeah, the volatility decreases, yes. And then that's because the van der Waals increase, yes. Why do the van der Waals increase? In number of electrons. That's good. Now it sounds like there's a class here. All right. Are we good with that? Now, chlorine undergoes disproportionation during chemical reactions. Write an equation for cold aqueous sodium hydroxide. Now, this is one of those things you've just got to learn. Sodium, I'm going to do it here. Sodium hydroxide is going to react with chlorine. I'm awful at inorganic, but yeah. Now you've just got to know these, eh? So you get sodium chloride and sodium hypochlorite. It used to be called sodium chlorate. And if in doubt, there's always often a water hanging around. Yes. So I've got to balance this now. I've got to put a 2 there. Is that good? Yeah. So I think that's the equation, isn't it? So why is this a disproportionation? Well, we've got chlorine as 0 on the left. We've got chlorine as -1 on the right. And this one, if you work it out, is +1. Yes. So the chlorine, CO2, is reduced to Cl minus, which is oxidation number -1. And it's also at the same time oxidized to Cl plus. Oh, OCl. Oh, I've messed that up, haven't I? It's OCl minus. And if this has an oxidation number of +1. Any questions there? Are we all good? Yeah. I'm going through this quickly. This isn't supposed to be teaching you chemistry. This is supposed to be kind of revising. Yes? Oh, oopsie daisy. All right. Now, if you do it with hot sodium hydroxide, you get a different thing. And again, there's nothing clever here. You just got to know what it is. And it's this one, isn't it? NaClO3. And if you work out the oxidation number of the chlorine there, it is +5. This one is called sodium chlorate 5. And the other one, the NaOCl, is known as sodium chlorate 1. Okay, are we good? Yeah, excellent. All right, there you go. So that's the first page done. Right, the next one is state and explain the use of chlorine in water purification. Right, now when you dissolve chlorine in water, this leads on from the previous one a little bit. I guess it does a little bit. When you dissolve chlorine in water, okay, you should all know this equation as well. And I'm pretty awful at inorganic, so maybe I won't get this. You get HCl, yes, and you also get this one. Okay, does that make sense? So this, I think, this is a disproportionation as well, isn't it? All right, if you look at this. So dissolving chlorine in water, you get two acids, don't you? And these are hydrochloric acids, and this one is known as hypochloric or something like that. I can't remember. Is it something like that? Hypochloric acid or hypochlorous acid? I think it is. All right. Anyway, so these acids are formed when you dissolve chlorine in water. And why is that good? That's one mark, by the way. Second mark would be, well, it kills bacteria, yes? Because don't forget, we're using it for water purification. Is that all right? Yeah. If you have a problem, stop me. Even though we're recording this, so but you can still stop it. All right. Under certain conditions, chlorine undergoes a free radical substitution with the reaction with ethane. State the conditions for this reaction to initiate. Well, the conditions for that are yeah, yeah, sunlight or a UV light, aren't they? Right, and that's all you got to do. Yeah. Write the overall equation for the reaction for the free radical. Now we start off with ethane this time, which is C2H6. We're reacting it with chlorine, Cl2. We end up with C2H5Cl and HCl. Okay, makes sense? That's a free radical substitution. Let's have a look at the next one. Okay. Oops, I've written those in already. Let me get rid of those. All right, I forgot to get rid of these for earlier, but never mind. Okay, there we are. Now, let's do the bonding first. Bonding in Na2O. Well, I'm going to guess ionic. Ionic is a pretty good bet for that, isn't it? Magnesium oxide is ionic. Aluminium oxide is ionic. Don't forget, it's not the oxide that's half covalent, is it? It's the chloride that's half covalent. The oxide is pretty well all ionic. Does that make sense? The chloride has mixed bonding. The oxide doesn't. Okay. Oh, I don't know where that funny noise came from. Right, silicon dioxide. That's covalent, isn't it? And sulfur trichloride, that's going to be covalent as well. What's the structure? Well, this is giant ionic, isn't it? So giant for ionic things, they're all giants. The structure is a giant structure. Giants. And the silicon dioxide, well, it's giant covalent, isn't it? But it's still giant. So I'm going to write giant covalent. And the sulfur trioxide is simple covalent. Simple molecular is probably a better term because we've already used the word covalent. Simple molecular. Okay. Explain why the boiling point of SiO2 is much higher than SO3. Sorry. Well, first of all, I think you should state the bonding type in them both. So SiO2, we're breaking what bonds? Yeah, we're breaking covalent bonds in this, aren't we? But to do the SO3, we're breaking van der Waals, aren't we? Yes. So how do you spell van der Waals? That's close enough for me. We're breaking van der Waals. So that's a statement of fact, but you've got to pull the trigger on the answer, and then you've got to say covalent bonds require more energy to break. Okay, and therefore they're going to have a higher boiling point. Okay. Now, oh gosh, what's all this? I thought I got rid of this, but I think it auto saved it, but maybe it didn't, or maybe it did. And that's why I've got them. All right. Explain what we mean by amphoteric. Now, amphoteric is obviously it reacts with acids and alkalis. Yes. All right. So let's move that up. It's going to react with acids and alkalis if it's amphoteric. That's what amphoteric means. All right, and then it wants equations to prove it. Now, the easy one is this, isn't it? Aluminium oxides plus HCl. That's going to give me aluminium chloride plus water. All right, now we've got to balance it. I need 3 of those, do I? Oh, no, I need 2 of those. Therefore, I need 6 of those. And therefore, I need 3 of those. How is the aluminium oxide acting there? It's acting as a? Yes, it's an oxide. It's acting as a basic oxide because it's reacting with an acid, yes? And so aluminium oxide will be acid soluble. Okay? It's acid. It will dissolve in acids. Now, the nasty one, how are you going to do it? Now, I don't know the answer to this. Aluminium oxide plus sodium hydroxide. I know you get sodium aluminate, yeah, but I honestly can't remember this equation. So if you don't know that equation, you should know that equation. Does that make sense? I know I'm being bad here, aren't I? But this is not about revising the subject. It's going through a paper, finding out what we need to revise, and doing as much stuff as we can. So that's something we should look at. One of them's easy. How does aluminium oxide react with sodium hydroxide? I don't know. I know it forms sodium aluminate, but trust me, there are thousands of aluminates. There's no one formula for aluminate. Okay, it's a ceramic, and there's loads of them. So I just don't know that. But we'll look at that another time. So you should put that away and write down somewhere. Got to learn that equation. State what you observe when a small sample of sodium oxide is placed in water. Right. Well, first of all, it's going to dissolve. Okay, because all group 1 things are soluble. Yeah, and it's going to form sodium hydroxide. So there's going to be a chemical reaction. So heat is going to be given out. Heat is going to be evolved. Okay, I've seen the answer scheme. That's all that they only wanted one of those 2, but you'll get heat involved. Is there a gas given off? And the answer is no, there is not. And we'll prove it to each other by saying sodium oxide plus water. It simply gives sodium hydroxide. There's no gas there, is there? Yeah, that's why sodium oxide is basic, and when it dissolves in water, it forms the hydroxide, which is obviously a soluble base, so it's an alkali, isn't it? Let's move that up. Here's the next one. All right. Now, what's the shape of an Sc selenium hexafluoride molecule? Yeah, I'd go for octahedral because it's coordinate 6, isn't it? Okay, so there you go. So write down octahedral there while I'm getting rid of this rubbish. Okay, now Gaseous, whatever that's called. I'll do this carefully. Gaseous selenium oxide reacts to form a polymer. On the left is the molecule. On the right is the polymer. And in the reaction, one Se double bond oxygen is replaced by two of those. You can see that, can't you? We break one of those and we make two of those. There's one we make, yes? And there's the second one we make. All right, makes sense. But it tells us there anyway. How much does it cost me to break one? Whoopsie daisy. Yeah, it cost me 514 to break. All right, and I'm going to add that. How much is it going to make? What am I going to do? I'm adding it to 2x, aren't I? If that makes sense. Does that make sense? That's two selenium oxides, yes? I'm adding it to two of those, and apparently I get minus 346. If you work all of this out, you'll end up with minus 430. Yes, trust me, yes. But don't forget, bond energies are all positive, aren't they? All right. So even though you end up with a minus thing, the reason you end up with a minus thing is because you have to put it in as exothermic in this equation to give you this. All right. So we find out the bond energy is actually 430 kilojoules per mole. All right. Now, I think this is the last one that I scribbled on. Yeah, I think so. Or maybe not. All right. Now, I want to get rid of this before we talk about it because it's quite a nice one. Okay. It says this selenium oxide shows similar chemical reactions to sulfur dioxide. This is inorganic, isn't it? It's not everyone's favourite subject, I must admit, inorganic. Suggest an equation to show the reaction of selenium oxide with aqueous sodium hydroxide. Well, I don't know what the equation is off the top of my head, but it says it's similar to sulfur dioxide. Okay, and I should know my sulfur dioxide. So let me do my sulfur dioxide. Sulfur dioxide. I know it reacts with sodium hydroxide. I know sulfur dioxide is acidic, and I know sodium hydroxide is basic. So I know I'm going to get salt and water out of it. Now the salt is going to be sodium sulfite plus water. Now I think, do I need two of those? And I think that's balanced now. Now I think it's balanced. It looks balanced. Yeah, I think it's balanced. Now, why do I know I get sodium sulfite? Well, what you do is you look at the oxidation number in your sulfur dioxide, and it's +4. And you go over here and you look at your oxidation number of sulfur in sodium sulfite, and it's +4. This isn't a redox reaction. Do you understand? It's an acid-base reaction. Yes? So it keeps the oxidation number. So SO2 will give sulfites, SO3 will give sulfates. Does that make sense? Yeah, so if I used SO3 here, I'd end up with sodium sulfates. So be careful. Care over these things. Now, well, that's not even the question, is it? The question is, what if I had selenium oxide? So what I do now is I simply copy that equation, but instead of SS, I put Se. So let's have a look. So it's SeO2 plus, even the balancing I don't have to worry about. Gives me Na2SeO3 plus H2O. You see what I mean? So why did that potentially awkward question become quite easy? Because I know I use this information. I use the fact that it's like silicon sulfur dioxide. All right, hope that makes sense. Okay, next one. Crude oil is a natural something or other. Let me get rid of this first. Crude oil is a natural source of hydrocarbons that are used as fuels. Hydrocarbons with a low relative molecular mass are used in the fuel industry, in home, and for transport. There is a high demand for the hydrocarbons with low molecular mass. Okay, we got to figure that out in a minute, but they want a low molecular mass is a good thing. Name the process by which long hydrocarbons are broken up into small ones. That's cracking. Yeah, so we can put cracking there. Give one reason why hydrocarbons with a low molecular mass are suitable for use as fuels. Now, because they have a low mass, yeah, if there's a 1 mole of methane, yes, which is a low 1 mole of methane, which is a low molecular mass, has a mass of 16 grams, yes. 1 mole of octane, C8H double it 16 add 2 18, yes, has a mass of, I have no idea, but it's a lot more. Do you understand? So for the same mass, you get more moles. Does that make sense? Yes. And because of that, the similar mass, if you have a low molecular mass thing and a high molecular mass thing, but for 1 kilogram of each, the low molecular mass thing will give off more energy. Does that make sense? Because it's got more moles in. Does that make sense? Okay. So low molecular mass, they have, I don't know if you should say this in the exam, but I'm going to say they have a higher energy density. You can, there's, it's absolute. If you want to say what I've just said, yeah, do you understand what I've just said though? Yeah. What's the best fuel then on that argument? Anyone can? Yeah. Well, no, not methane. The best one I can think of is hydrogen because it has a mass of 2, doesn't it? So if you've just got 5 or 6 grams, 6 grams of hydrogen is nothing. You know what I mean? 6 grams is nothing. You understand me? But if you have 6 grams, you've got 3 moles. Yes? If you have 6 grams of methane, you've got less than half a mole, haven't you? Do you know what I mean? So there you go. So incomplete combustion. Let's now it wants us to incompletely combust. What is it? Incompletely combust what? Butane. So let's incompletely combust butane if we can, if we quit very quickly. Right, I'm going to draw butane. So C4H8. I'm going to react it with oxygen. And then I'm going to say, instead of getting carbon dioxide, I'm going to get carbon monoxide. And I'm going to get water. All right, so you get those things. Now, the awkward thing is we've got to balance it. So I need a 4 there. So we've got 8 of those, 4 there. 4 plus 4 is 8. I think there's a 4 there. Yeah. Oh, I've done it in the wrong place, haven't I? Yeah. Sorry about that. This should go there, shouldn't it? Yeah? Makes sense? Sorry about that. Right, identify an analytical technique that can be used to monitor the levels of carbon monoxide in the atmosphere. Outline how this analytical technique may be used to monitor the levels of CO, sorry. Right, now, the only analytical thing you've done really is infrared, yes? So the technique is infrared spectroscopy. Okay. Outline how. Well, what it will do, the carbon monoxide, the C triple bond O will absorb certain frequencies. Make sense? It will absorb a certain frequency. So if I have a sample of air and I test it with infrared, if it doesn't absorb at that frequency, there's not much carbon monoxide. If it has a deep absorption at that frequency, it shows there's more carbon dioxide. Does that make sense? If you don't follow that, look it up and you can learn a little bit more about it. And then this is, here we are. Thioprene is an organic compound that's found as a contaminant in crude oil. Construct the equation for the complete combustion of thioprene. All right, anything with thio in has sulfur in. I've done it there. Let's do it again because it looks complicated, but it's not. All you've got to do is this. All right, let me write down the thioprene. It is C4H4S plus O2. And if I completely oxidize the carbon content, I'm going to get CO2. If I completely oxidize the hydrogen content, I'm going to get water. And if I completely oxidize the sulfur content, I'm going to get SO2. Yes? Interestingly, when you burn sulfur, you don't get SO3. The only way you get SO3 is using a catalyst. It's quite hard to get SO3. All right. If you burn it, you only get SO2. To get to the SO3, you need a vanadium pentoxide catalyst. Yeah. Now I've got to balance it. Oh gosh, here we go. Right, 4 of those, so 4 of those. 4 of those, so 2 of those, I think. 1 of those. 2, that's 4, that's 8, 9, 10, 11, 12. So I think it's 6 there. Okay. But you can balance that yourself if you have a problem. Student carries out an experiment to determine the enthalpy change of combustion of that, explaining the meaning of the enthalpy term of combustion. Right, what are the pivotal points there? Well, we're burning 1 mole, aren't we? 1 mole of compound, that's pivotal. Yeah, exactly. In excess oxygen under standard conditions. I think that's good enough. All right. Now I'm going to clean it up again. I'm going to say that it is the enthalpy change when. Okay. So as long as you get the pivotal things, the 1 mole of compound, excess oxygen, standard conditions, I think you're good. That's all you got to do there. All right. Let's move this up. Oh, there we are. We got a thermometer of some description. The student uses the following apparatus. There's a copper container. There's a thermostat. Thermometer. There's a water. There's some fuel, and that's burning this stuff. A mass of water in the container is that. Initial temperature is that. Highest temperature of the water is that. Calculate the heat energy released in joules by the reaction, and there we've got bits and pieces there. Right, now, as we've said 1,000 times, everyone, let's go to a different colour. Let's go to dark blue. All right, now, all it wants is the heat energy, so it's Q, is mc delta T. M is the mass that you're heating up. It's not the mass of the fuel, it's the mass of the water you're heating up. Yeah? Please don't forget that. C is 4.18, apparently. And delta T, I have no idea. Because someone do it for me, which is 37.5. Take away 18.5. What's that? 19? Is it 19? Yeah. All right. So then you do that for me, please. 200 times 4.118 times 19. Sorry, dear? 15,884. 15,000. Oh, that's a lot. All right. Does that have a sign to it? Yes or no? No, it doesn't. It's energy. Energy is not it's not vector. Yeah, it's just an energy given out. All right. The student used 0.63 grams of that in the experiment. Calculate the enthalpy of combustion. Now, all we have to do now is scale that 15,884 up to a mole. Yes. Now, I don't know what the relative molecular mass of this is. So the first thing we've got to do is find out the relative molecular mass of this. Right, see if you can do it quicker than me, unless it says it somewhere. Oh, 32, dear. Sorry, dear? God, you're good at this. 4 times 12 plus 4 plus 32. Oh, I'm not going to bother with the point ones and stuff. So what is it, 84? Well done. So then I would say this. This is the scaling up. I could convert it to moles, yes, but I'm going to leave it in masses. Does that make sense? So 0.63 grams give me that number of joules, and therefore, 84 are going to give me this number divided by 0.63 times 84. Yes? So is that right? I think that's right. So figure that out for me. It's going to be quite a big number, very big number. This is in joules, though, isn't it? The way I've done it, yeah? So what is it, anyone? Don't forget, and then you divide the answer by 1,000 to get kilojoules, yes? Because the answer must be in kilojoules. 2118. That's huge, isn't it? 2118, and the sign? It is negative because it's exothermic. And it does say, include the sign, which most of you forget. Okay, next. Oh, thank God, a bit of organic. Good thing about organic is it's quick. Give the name of that. Well, it's an aldehyde. I don't know the name of that, so I'm going to have to write it out. Okay, so we've got this thing. There's the aldehyde bit, and it's connected to three methyls. So there's one there, one there, one there. All right, that's all I'm going to do. I'm not going to bother with the hydrogens. So let's name this. Well, that bit is called propanal, isn't it? Okay, and we have two methyls on our propanol, yes. So we've got dimethyl, and they're both on number two. All right, and we count from this side, by the way. We count from the aldehyde side. So they're both on number two. So this is 2,2-dimethyl propanal. Don't forget that's an A there. All right, good. State hybridization of carbon labeled with an asterisk. Well, that's one we've done a million times. Anyone? It's sp2 hybridized. Well done. Okay, sp2. Let's mess around while we're there. These bond angles are 120. And this one is sp3. And these bond angles will be 109 and a bit. Okay, I think that's all the only bond angles there. Two reaction sequences are shown. Whoopsie daisy. All right. I think I'm getting. Let me make it a bit smaller. Two reaction sequences are shown. We've got our aldehyde going to S, and we're treating it with NaBH4. Yeah. What does NHBH4 do? Yeah, it reduces it. So the aldehyde will reduce to what? Primary alcohol. So let's draw it while we're here, because maybe if we draw it here, we don't have to draw it later. Oh, I don't know what I'm doing there. Let's start again. Sorry. Right. Let's have a different color. Let's have green, dark green. Yeah. Okay. So I'm going to put CH3. You can. I hope you're keeping up with me. Yes. All right. Keep up because that's why you've got the papers. CH3, CH3, and this becomes CH2. OH, doesn't it? And this is without even looking at the questions because we're going. Hopefully, we're accidentally answering. This is a reduction, isn't it? Now we're oxidizing this, and this is an aldehyde group, and it oxidizes, as we thought, to the carboxylic acid, yes? All right, and then presumably it's going to ask us how we do this, but we'll see in a minute. And then we reaction two with this. Now it's done something nasty. It's gone from a condensed formula to a skeletal formula. But we should be able to see the functional group there. What's that? That's an ester. So what is reaction two? What did I add to it? An alcohol. And this is the alcohol, isn't it? Can you see the alcohol? Can you tell me the name of that alcohol? It's definitely three. Huh? Right. Listen. Can you see the alcohol? So you can see it. How many carbons are there? Three. So it's propan, isn't it? Propan. Now, where was the OH though on the alcohol? It's number two. So it's propan. Yeah, it's propan two. This is number two. Is that good? Yeah. Yes. I don't know. We're going to name it. Let's hope not. We'll see. Yeah. I know what you mean. Yeah. It's a very good point. Okay, we'll see. Okay, I don't know. I think I know what you mean, but I see. But I'm not big into that. Identifying, but it's a good question. Yeah, maybe I'll dig it out if we get time in Chem Sketch, because I don't know the names of these things either. But we'll dig out a name and see if how far we go. Reaction one: identify the reagent. So what would you do for reaction one? Yeah, don't forget you identify the reagent. I would use potassium dichromate 6. Yes, it's aqueous, and I would acidify it. Well, this is you have to heat this up, dear. But what we're doing is we're oxidizing an aldehyde. Yes, makes sense. Yeah. Oh, reaction one. No, no. Oh no. I'm sorry. I was getting confused there myself. So we'd still use that. Yes. All right. Now, we want to keep everything in the container, don't we? We don't want it escaping. Yeah, so we'd use, well done. I was thinking that we wanted to take the aldehyde out, but we don't. You follow me? We wanted to get the acid out, don't we? So there you go. A is that. B is that. A is a solid at room temperature, whatever acid that is. B is an isomer. So we already know what it is, don't we, accidentally? It's an isomer of A. Oh, it's interesting. Um, is an isomer of A. B is a liquid at room temperature. Explain the difference in physical states of A and B with reference to any intermolecular forces that exist. Now, this is quite an interesting one because, as I've said before, and I'm sure I've said this before, if you have a carboxylic acid, yes, and an ester with the same number of carbons as that carboxylic acid, they will be isomers. Yes, it's a useful thing to remember. So if I'm talking about ethyl ethanoate, yes, will be an isomer of butanoic acid. Make sense? It's a useful thing to remember. Okay, so obviously A is the solids. So let's get a move on because I think we're a tiny bit behind time. Well, look at this thing here. There's an OH there, yes. So A is going to have hydrogen bonding, isn't it? Now, B doesn't have hydrogen bonding because it's an ester. So B is going to have dipole, dipole. Yes? So that's first things first. So you've got to mention what the intermolecular forces for them both are. All right? And then you've got to obviously state that hydrogen bonding beats dipole, dipole. Yes? And therefore, you're going to require a greater temperature to melt this. Greater temp to melt. Now, these ones, you've got to learn how to answer them. They're going to come up. So make sure you understand that. Give the balanced equation for the reaction of that with that to form S. And we can use H as our reducing agent. Okay, so let's have a look at this. CH3, 3 times, CCHO. And this, what are we adding on? We're adding one, oh gosh, I'll have to write this out because I'm horrible. So we've got that. We've got that to start with, I think. Yeah, there's a C there, a C there. Yes, makes sense? We start off with that, yes. And this bit becomes that bit. Yes? All right. Okay. So what we're doing is we're reducing it. So how many hydrogens have I added? Yes, we've added 2. Now, you know what? If you're not careful, you're going to say 3. You with me? Is everyone with me? So look at that. There was one there already. Yeah, and we've added 1, 2. So here we say plus 2 H's. Make sense? Yes? Like that. And then I can say CH3 3 times, CH2OH. I think that looks right. If anyone wants to correct me, please do. But that looks okay to me. All right. Now let's move on. Draw the structure of the organic molecule T that reacts with A in reaction 2 to form U. Crying out loud. I think, unless I'm wrong, that was our propan 2-ol. Yeah, it wants the structure. Now draw the structure. I can be cheeky and I can simply do that. Yes, which is propan 2-ol. All right, and if you want to be a bit cleverer, you can do more things. Are you with me? But there you go. What's the catalyst? Well, the reaction is an esterification, so the catalyst is conc sulfuric acid. Now listen, if you write that down, you'll get 1 mark. Yes. If you write this down, you'll get no marks. Is that clear? Because you weren't looking. If you imply water, this contradicts this. Yes? And they're very picky on that, so don't put water. Okay? All right, are we good? All right, let's move up. Okay. X, Y, and Z are isomeric forms of that, which is the aldehyde. And we've got a summary of the reactions and properties of X, Y, and Z are shown in the table. Observations with 2, 4, 6 p.m. X, Y, and Z are isomers of that, yes? So when you've got an aldehyde, yeah, an isomer of an aldehyde is a ketone, yes? So one of them is going to be an aldehyde, one of them is going to be a ketone. There you go. All right. Now I'm looking because I'm pretty good at IR and I know the numbers. Okay. I'm looking at these numbers here. And one number that should flash neon signs is this one, the carbonyl group, the CO. And that one is such an obvious one. It's around 1700. Yes? And if you just know that alone, you'll answer 80% of these questions. Oh, there's one in this compound. There's one in this compound, but there's none in this compound. Yes? So X, Y, and Z are isomers of that. A summary of some of the reactions and properties are this. Okay? So I get a red precipitate with phthalins. So that tells me Y must be what? It's a positive test with phthalins. Yes, right. It's the aldehyde. And it is, in fact, this guy. Fair enough? Yes? Fair enough? CH3. Oh, isomers of it. Sorry, I'm confusing you. I don't think it means that is one of them. Do you follow me? All right. So I'm going to cheat and I'm going to stretch this out and I'm going to say 1, 2, 3 for those three, 4 for that one, and then this one. Make sense? Yeah? So I'm going to say that. All right? That's going to be my Y. But I'm doing the question wrong, aren't I? Because it doesn't want the structure, which I've just seen. So it wants the observations with 2,4-DMPH. 2,4-DMPH sniffs out what? Sniffs out carbonyl groups. So both of these, as I've said, have a carbonyl group, don't they? So both of these are presumably going to have, an orange PPT. Orange PPT. Fair enough. Yeah, we good. X and Y each contain a carbonyl group. Oh, well, that was, I don't know why I bother with this because I think we're making it harder than it should be. X and Y contain a carbonyl group, which we knew already, didn't we? Complete the table. All right then. Right now, where are we? How close did we get? That, ladies and gentlemen, was the last page anyway. All right. So off you go. Oh, let's try and finish it because I think Mamia's on the way, isn't she? Oh, is there? That's annoying. Is there? Oh, there is. Oh, I thought, oops, I thought we got there. But let's go. Let's see if we can do this page, and then maybe you can do the last page with her. All right, complete the table. We've done that. Identify the functional group present in Y that causes the recorded observation. What is the functional group? As Basadi said, it's the aldehydes. All right. I don't know why that's not writing. Aldehyde. My pen's gone weird. The aldehyde. Y has a chiral center and exists as a pair of optical isomers. What do we mean by a chiral center? It's one connected to 4 different groups. Yeah. Now you can draw the optical isomers there of Y yourselves. All right. Now the very last page, which hopefully is this the last page? So this. Anyway, we nearly got there, didn't we? We were a couple of short. All right, now I'm going to do the first bit, and you should know these really. Bond responsible, yeah, this is an OH bond. Whoops, I shouldn't draw that. That's confusing everyone. So they want a specific bond, eh? So you've got to do OH. Don't connect anything else. 1630, well, you'll look it up on the book, yes. I don't know what that is off the top of my head. 1050, you can look that up. All right. Hold on, everyone. Let me turn the recording off.